For the purposes of analyzing SN2 reactions, we also need to consider the substrate itself, which is to say the carbon that the leaving group is bound to clearly plays a role in how fast an SN2 reaction takes place. And so the substrate effects are pretty simple. Methyl beats primary, which beats secondary, which beats tertiary, and in fact, tertiary is so bad that we essentially consider no tertiaries ever react via an SN2 reaction. Again, the smaller the group that the leaving group is bound to, the faster this reaction goes. And methyl and primary are pretty darn good, secondary is dramatically slower, and tertiary is so slow that it basically never happens. So why is that? Well, in all cases, you have nucleophile floating around out here, and it needs to get access to the backside of the carbon leaving group bond. Right here, behind this carbon, is a lobe for the sigma star that's going to need to be attacked. And in the methyl case, you can see that those hydrogens really don't get in the way very much. It's easy to gain access to that orbital, and it doesn't matter what the size of the nucleophile is, to some extent. The nucleophile can get in there relatively well, or at least the atom of the nucleophile can get in there and work. Whereas, as soon as we start turning this into a methyl on top, so this is now a primary system, then there's at least some steric hindrance for protecting the back of this from attack. So there's a chance that the nucleophile encounters this hydrogen. There's a chance that the nucleophile encounters this hydrogen and bounces off, and we call that term steric hindrance. This is, of course, the sterics in rows. Finally, of course, if we have a tertiary system, then that means that literally every atom back here is offering some significant resistance to accessing the orbital that we need to. And again, there's a tertiary system. For all intents and purposes, we claim that you cannot do SN2 chemistry on tertiary systems. So again, the idea here is that we have simply a methyl chloride or something like that, and the nucleophile needs to be able to access this area right here, and the hydrogens really don't preclude that from happening. You can get access easily enough. Whereas in the tert-butyl case, there's a lot more hindrance, there's a lot more difficulty having the nucleophile come in and bind back there. In fact, if I use the methanol coming in to interact, you can see the potential issues right away. Tertiary systems, generally speaking, do not react via SN2 type reactions. Primary systems, or methyl systems, have no such difficulties. This is a methyl chloride, and here's the primary system. Though there's now much more steric hindrance than in the methyl case, you can still access this trajectory and get at the backside of this molecule fairly easily. Whereas once you have a tert-butyl in place, then you can't get access to the necessary sigma star orbital. So as we now gaze upon the glory of my super nerdy t-shirt, I hope you see what the problem is. We can imagine this molecule right here, the nucleophile, as being, say, a methoxide. It's not entirely clear to me whether that's supposed to be an oxygen or not. But anyhow, this is the nucleophile, methoxide, and it's trying to attack what is very obviously a tert-butyl chloride. This isn't going to work. So I love this shirt because it's a chemistry nerd thing, but unfortunately, there should be a big red X through there that's saying this can't happen because SN2 reactions don't happen on tertiary substrates.